5.3, Part 2, Inverse Functions. We're going to start with the theorem, 5.8, the continuity and differentiability of inverse functions. Are inverse functions all continuous? Are they all differentiable? Let's talk about it. So f is a function whose domain is some interval I. If f has an inverse, then number one, if f is continuous, then the inverse of f will be continuous. If f is increasing, then the inverse will be increasing. Likewise, if f was decreasing, then the inverse is decreasing. And remember, a function can only have an inverse if it's always increasing or always decreasing on its entire interval. And then number 4, if f is differentiable at a certain number, and that derivative does not equal 0, then the inverse is differentiable at that number. Just a few things to remember about the relationship between original functions and their inverses. Another theorem is the derivative of an inverse function. Of course, we had to get to that. It's calculus, right? Let f be a function that's differentiable on I. If f has an inverse function, we'll call it f to the negative 1 or f inverse. Then f inverse is differentiable at any x for which the derivative of the inverse at that x does not equal 0. Because here's the key feature. This notation means the derivative of the inverse at x. This is the inverse, and this prime means the derivative of the inverse at x. So the formula for the derivative of the inverse at x is 1 over the derivative of the inverse of x. So it's a composite function in the denominator. This is the original function's inverse. This is the original function's derivative. And you put the inverse inside of the derivative. All right? Usually we won't have to do that numerically. The reason we use this type of formula to find the derivative of the inverse is if you can't actually find the inverse using algebra that you know. Reviewing from yesterday, when you want to find the inverse, you switch the x and y and then solve for y, or solve for x, or switch the x and y and solve for whichever order you want to do it in. You can solve for x first, then switch the x and y, or switch the x and y and then solve for x, or solve for y. Whatever order you want to do it in. Sometimes that doesn't work, but you might still want to be able to find the derivative of the inverse. So even if you can't find the inverse function itself, you can still find the derivative. For example, this function here, we could not find the inverse using algebra that we know. But we still might need to find the derivative of the inverse at a certain point. So we're going to use this formula that the derivative of the inverse at 3 would equal 1 over the derivative. What? All right, sorry about that. So our formula is the derivative of the inverse at 3 is 1 over the derivative of the inverse at 3. So what we're asking to do is plug 3 into the inverse function, which we can't find, and then take that answer and plug it into the derivative, and then finally do the reciprocal of that answer. So how are we going to do that? Let's think about what we know about inverses and original functions. Their domains and their range flip. So if I want to plug 3 into the inverse function, 3 would be in the domain, that's the x value, and I'd be plugging that into the inverse function. So if you've got a little table over here, I want to plug 3 into my inverse function. Well, thinking about the original function, that means that I don't know x of the original function, but I know that the f of x will be 3. So I know that if I have my original function, I want the y value to be 3. So how can I find the x? Because once I find the x for the original function, that will be the y value of the inverse, because the x's and the y's switch places. So how can I do that? Look on your graphing calculator. So we're going to graph y equals x to the, or 1/4 x to the third plus x minus 1. And we're also going to graph 3. Or you can set this equal to 0 by subtracting 3 and just graphing this and finding the zeros. But I'm going to find the intersection, so number 5. It intersects at 2. So I know that x will equal 2. So when the y value is 3, I know the x value is going to be a 2. So in the inverse, if the x value is 3, the function, or the inverse function at 3 will be 2. So now I know that this part equals 2. So now I need to find the derivative of the original function at 2. All right, let's go back to the original function and find the derivative. The derivative of the original function is multiply the 3, so it becomes 3/4 x squared. Derivative of x is 1. Derivative of 1 is 0. So 3/4 x squared plus 1. I want to plug 2 into that. So I'm going to have 3/4 times 2 squared plus 1. 2 squared is 4. 3 times 4 is, 3/4 times 4 is 3. 3 plus 1 is 4. So that's the answer that I wanted. And I didn't even have to find the inverse function. I just used what I had based on the original function, setting it equal to the y value that I wanted, and taking the derivative of it and using this formula. You will have to memorize that formula. So let's do another example. If I want to find the inverse derivative, the derivative of the inverse of a, if f of x is 2x to the 5th plus x cubed plus 1 and a is -2. So I want to find the derivative of the inverse at 2. That will equal, because I can't find the inverse of this. You could not set this, you could not solve for x here. So that will equal the derivative of the inverse at -2. 1 over the derivative of the inverse. No, 1 over the derivative of the original with the inverse plugged into it. All right, so I need a couple things. I need to talk about my original functions, x and y's, and my inverse functions, x and y's. If I want to plug -2 into the inverse, that means -2 is the x value, and I want to find that y value. So if -2 is the x value of the inverse, then it will be the y value of the original. So I'm going to plug that in for the y and solve for it. Again, I'll use my calculator. So I have 2x to the 5th plus x to the 3rd. I'm not used to my new software yet. I keep forgetting to get out of the exponent. That looks better. I knew it was missing half the graph, I just didn't know why. -1. So x equals -1. So my original function, when my y value is -2, I know my function x value is -1. So that must be a -1. So now I can plug in -1. That's what that is. That's the y value when x is -2 in the inverse. So now I need the derivative. The derivative of my function, the original function, is 10x to the 4th plus 3x squared, and I'm going to plug in a -1 to that, which will equal 10 plus 3. So that would be 13, so it's 1 over 13. So my final answer is 1 over 13. Another key inverse relationship is that the graphs of inverses have reciprocal slopes at their corresponding points. So if the derivative with respect to x can be written as 1 over dx dy, it's the reciprocal of this, it's 1 over the reciprocal. So the slope of the original equals 1 over the slope of the inverse. And this is a notation for the slope of the inverse function of y. You can write it like that. So if dy dx equals 8x over 7, then dx dy equals 7 over 8x. They're just reciprocals at their corresponding points. So let's say we've got a function f of x equals x squared, and the inverse is the square root of x for all x is greater than or equal to 0, right? The slope of f at 2, 4 is what? So let's take the derivative of f. It's 2x. So the slope at that point, 2, 4, is actually 4. So the y value is the same as the slope. Now the rule we just learned is that at the corresponding point, which is the 4, 2, see these two are the corresponding points, this should be the reciprocal of this slope. So it should be 1/4. Let's see if we get that. So since this function already has its inverse, we can take its derivative. So let's take the derivative of the inverse. It's 1/2. Subtract 1 from the exponent, and then multiply by the derivative of the inside, which is just x. So that equals 1/2 square root of x. At the point 4, 2, that would evaluate to 1/2 times the square root of 4, plugging 4 in for x, which is 1/2 times 2, hey, which is 1/4. So we got it. So the derivative of f at 2, 4 is equal to the reciprocal of the derivative of the inverse at the corresponding point 4, 2. Another example of finding the derivative of the inverse using the formula. We're going to do it at 1 here. Using the formula, 1/f prime of the inverse. So let's see, what should we do first? We can find the derivative first if you want. The derivative of cosine 2x. 2x is the inside function. So the derivative of the outside would be negative sine 2x, and then times the derivative of the inside. So I would write that negative 2 sine 2x. Okay, we also need to talk about the original function, their x and y, and the inverse functions, x and y. The x we want to plug into our inverse function is 1, so that's going to be the y value of our original. So I need to find this, which will help me find that, because that's what I really want. So where does cosine 2x, the original function, have a y value of 1? Thinking about your unit circle, where will the cosine be 1? Well, here's a place, and here's a place. Now I know the domain says the x's have to be between 0 and pi/2, but right now we've got a 2x here. So 2x could equal this 0, because cosine of 0 would be 1. So then if you solve this, you divide by 2, you get x equals 0. Cosine of pi is also 1. Whoops. So 2x could be 2x could be pi also, because that point right there has a cosine. Never mind, it does not have a cosine of 1, it's negative 1. All right, that's our only place where cosine has a value of positive 1, and that is in this domain here, because 0 is included. So x is 0. When x is 0, y is 1 of the original function. So when x is 1, the y must be 0. So we can plug that in here. 1/f prime of f inverse of 1 is 0. We just found that. So we're going to do the derivative of 0. 1 over, and then sine of 2 times 0 would be sine of 0. Sine of 0 is 0. Negative 2 times 0 is 0. Hey, you can't do that. So there is no answer for that one. Why is there no answer for that one? Remember, way back here, we talked about how that denominator could not equal 0. So if this denominator equals 0, then the function, it doesn't, then the inverse does not have an answer for the derivative at that point. It's not differentiable at that point. So the inverse of the example we just did is not differentiable at 1. That's what we say. Okay, let's talk about finding the domains of f and f inverse, and then finding the ranges of them, and then graphing them. So thinking about domains, what number could I not put in here? Normally we think about the domain being all reals, but we do have a denominator, so we have to be wary of the fact that that denominator cannot equal 0. Is there an x value I could plug in here so that when I square it and add 1 to it, it would equal 0? Well, 1 plus negative 1 would be the only way to get a 0. And you can't have a negative 1 come out when you square it in real numbers. Imaginary numbers would work, but we're talking real numbers here. So the domain here is all reals, because there's never a problem. We can put any number in here, square it, and add 1 to it, and we'll never equal 0. All right. This one, however, you cannot have a 0 in the denominator. So x cannot equal 0 here. And also, here, we can't have a negative inside the square root. So let's look at this square root here. We know that what's inside the square root can never be negative. So let's simplify a little bit. We have 1 over x minus x over x, and we want that to be greater than or equal to 0. That simplifies to 1 over x minus 1. So if you add 1 to both sides, you get that, and multiply both sides by x. You end up with 1 is greater than or equal to x, or x is less than or equal to 1. So think about numbers less than 1, but we don't want to go below 0, because if you pick numbers less than 0, like 1 minus a negative 1 over negative 1, dividing that by negative 1 will end up with a negative inside the square root, and we can't equal 0. So really we just want numbers less than or equal to 1, but greater than 0. If you pick numbers greater than 1, think about that, like a 2, we'd have 1 minus 2 over 1, and that would be negative. So this is our domain for this function between 0 and 1, and the domain for this function is all reals. All right, so now we can go to look at the graph. Oh, let's talk about the ranges. So then the ranges would switch. So the range of the original should be 0 to 1, and the range of the inverse should be all reals. But let's look at the graph to verify that. Okay, one other thing we should notice is that this says x is greater than or equal to 0 here. So that means part of the domain is, or the domain looking at x is greater than, so all real numbers. We know all real numbers would work, but they want to just restrict the domain to greater than or equal to 0. So that will change our range to just be greater than or equal to 0. So now let's look at the graphs of these two functions on a graphing calculator. We're going to send to y1, and this one's going to be y2, and then we'll zoom in a little bit. This is what they look like. This arch here is y1, that's 1 over x squared, and you can see we're only looking at the domain is, we're just going to look at x is greater than or equal to 0, so we don't want any of this part here. And the range is from 0 to 1, not including 0, because it doesn't touch the x-axis, and it goes up to and including 1. And the graph does not go any higher than that. So right for y1. And then 2 is this line right here, and the domain we said is between 1, and you can see it doesn't equal 0 for the domain, but it does go down to equal 1 here. And if we restrict that range, I see this mistake here, that should be, range is obviously a y value, so that mistake should say y is greater than or equal to 0. So we've got the y values between, or the x values between, and the y values are equal to 0 and never than 0. So we did get it right. Just remember how composite functions work. If you have the function 1/8 x minus 3 and g of x equals x cubed, this notation means the composite function, the inverse of the composite function, g of f of x. This is the composite function f of g of x, could also be written like this. This is the inverse of f, the inverse of g, and then a composite function of those. And this means the same thing. Well, not exactly. They might not be equal. So different. This is the inverse of the composite function. So let's see if they're equal or not. So we need the inverse functions of these. So add 3 to both sides, multiply by 8, and switch variables. So the inverse of f is 8x plus 3. Here, solve for x, and switch variables. So the inverse, of g is the cubed root of x. So what's g of f inverse? So we need g of f. So I need the cubed root of 1/8 x minus 3. And then I need the inverse of that. So put y in. Cube both sides. Add 3 to both sides. Multiply by 8. Oops, that's 24. That doesn't equal f, that equals the inverse. G of f inverse. Okay, that's that one right there. This one, f of g of x, putting g of x into f, so we'll have 1/8 times x cubed minus 3. This one, inverse of f with g inside of it, with the inverse of g inside of it, so we're going to take that and put it inside of the inverse here. So it'll be 8 times the cubed root of x plus 3. F of g inverse means we have to do f of g first, which we did here, and then take the inverse of that. So I'm going to do that work over here. We want the inverse of that, so y equals 1/8 x cubed minus 3. That's f of g. Add 3 to both sides. Multiply by 8. Take the cubed root. So that would equal the cubed root. Switch your variables. All right, so that was a pretty long example. Just a lot of different ways of looking at inverses and composite functions together. There's your homework, page 350, 41 to 53 odd, 59 to 93 odd, and 99. Sorry about the long video. I threw an extra example in there, a couple extra examples just to show some different things that could happen with that derivative of the inverse thing. So good luck.